MCV4U1, Chapter 1, Session 13. In this lesson, we work on Section 1.6 from the textbook, and we discuss the meaning of continuity. The idea of continuity may be thought of informally as the idea of being able to draw the graph without lifting the pencil. The concept arose from the notion of a graph without breaks or jumps or gaps. When we talk about a function being continuous at a point, we mean that the graph passes through the point without a break. A graph that is not continuous at a point, sometimes referred to as being discontinuous at a point, has a break of some type at the point. The following graph illustrates these ideas. If you look at the graph of the function here in part B, it is discontinuous at x equals 1. The graph breaks at 1, and there is a hole on the graph of the function. If we look at on the graph in part C, the graph breaks at 1, and it is a jump discontinuity. And in part D, the graph breaks at 1. We deal with a vertical asymptote at x equals 1. Hole, jump, and vertical asymptote. The graph in part A is continuous for all values of the domain. Let's define the continuity at a point. The function f of x is continuous at x equals a if f of a is defined and limit of f of x as x approaches a exists and equal to f of a. If the limit of f of x as x approaches a does not exist, or f of a does not exist, or if they are not the same, then we say function is discontinuous at x equals a. Our first example here is a piecewise function. It is x2 minus 3 for x less or equal than -1. For x greater than -1, it is x minus 1. Determine limit of f of x as x approaches -1. When x approaches -1 from the right side, the limit would be limit of x minus 1 as x approaches -1 from right side, which is -2. The limit of f of x as x approaches -1 from the left side would be limit of x2 minus 3 as x approaches -1 from the left side, which is -1 to the power of 2 minus 3, again -2. Therefore, limit of f of x as x approaches -1 is -2. F of -1 is also -2. To find f of -1, we plug in -1 into x2 minus 3 because we have equal sign here. And f of -1 is going to be -2. F of x is continuous at x equals -2 since the right side, left side limit are equal, and the limit is the same as the value of the function at x equals -1. If we look at the graph of the function, we'll see the function is continuous at x equals -1. From the graph, limit of f of x as x approaches -2 is -1. F of -1 is also -2, and f of -1 is also -2. Therefore, the function is discontinuous since f of -1 and limit of f of x are the same. Polynomial functions are always continuous. Rational functions are discontinuous when the denominator is 0. Piecewise functions could be discontinuous at the point that the function's role is changing. F of x equals x3 minus x is continuous at x equals 2. G of x equals x2 minus x minus 2 over x minus 2 is not continuous at x equals 2. The limit of f of x, the limit of g of x as x approaches 2 is the same as limit of x plus 1 as x approaches 2, it is 3. Therefore, 2 and 3 is a hole on the graph of the function. The graph of g of x is a line, y equals x plus 1, with a hole on that at point 2 and 3. Part C, h of x equals x2 minus x minus 2 over x minus 2 if x is not 2 and h of 2 is 3. Basically, h of x is extension to g of x, and it is defined at 2 and 3. This function is continuous at x equals 2. Part D, f of x is discontinuous at x equals 2. X equals 2 is vertical asymptote of the graph of the function, and we deal with infinite discontinuity. Part E, left side limit of g of x as x approaches 2 is 0, right side is 3, therefore limit of g of x as x approaches 2 does not exist, and we deal with a jump discontinuity of this function. Let's recap. The function f is continuous at x equals a. When f of a is defined, limit of f of x as x approaches a exists, limit n of f of x as x approaches a equals to f of a. When we say limit of f of x as x approaches a exists, that means right side and left side limit as x approaches a both exist and they are equal. It's good to know all polynomials functions are continuous at any real number. A rational function is continuous at x equals a if the denominator is not 0 at x equals a. A rational function in simplified form has a discontinuity at the zeros of the denominator. When the one-side limits are not equal to each other, then the limit at this point does not exist and function is not continuous at this point. To understand what we discuss in this section, work on question number 4, part A, G and H. Question number 7, question number 8, and question number 11, page 52, exercise 1.6. Thanks for watching.